This is Rust in Production, a podcast about companies who use Rust to shape the future of infrastructure. I'm your host, Matthias Endler from Corrode, and today we are talking to Jakub Valtar from Fusion Engineering about flying drones with Rust. Jakub, thanks so much for being on the show. Can you introduce yourself to the audience?
Hi, thanks for having me. So my name is Jakub Valtar. I'm originally from the Czech Republic, and I've been with Fusion for almost 4 years now. About my background, originally I'm a software engineer with a focus on computer graphics. I can write game engines, and for a lot of time I've been writing interactive installations and been involved with the creative coding community. And later that's resulting in me going to art school and getting an art and technology degree, which I think is a nice way to round up my skill set.
Sounds amazing. I always was interested in the intersection between art and code, so I can totally relate.
Yeah, I think it's really interesting when code does something either physical or visual. For me, having a piece of software which outputs few numbers is not as exciting as when my software makes something really pretty or it makes something interactive which people can play with, or it does something like making things fly.
Exactly. That's a good prompt because you work at Fusion Engineering. So tell us a little bit about Fusion Engineering, the company you work for right now.
Yeah, so we're Fusion Engineering. We develop flight controllers, which little drone brains that control the whole drone. Our company was founded in 2017, and the original plan was to make drone for maintenance of wind turbine blades. The problem with wind turbine blades is that they get damaged by quite extreme weather. Salt, the leading edge gets damaged over time, and that reduces the efficiency of the whole thing. So normally you would take people up there and have them inspect the blades. Usually there's 3 of them, so they have to go up and down and manually inspect the whole blade. There are no physical defects there, and apply some coating to fix all the material issues with that. So with the drones, you could put the blade horizontally. You could land the drone on the blade, and there's a few different approaches. Either you have something which drives over the blade and inspects it, or the drone can fly by the blade and do some remote inspection using some maybe a laser scanner or something like that.
So if I understand correctly, it almost sounds like rocket science to me. Do you have these big turbines, wind turbines? And I never even thought about maintenance for these devices, but for sure, you need to get up there and you need to inspect those blades because, as you said, weather conditions and all of that stuff. And you can do that with drones. If you were to fly up there, you could inspect them, and it would save you probably a lot of time, and it would probably also be way less complicated than doing it by walking up there.
Yeah, so that's the thing. I'm not sure what exactly is the frequency of the maintenance, but you have to have people doing work in high altitude above ground, and that's dangerous. People fall. You need to do all of the logistics, like getting the equipment there. People need to eat and go to toilets and stuff like that. So you have to take breaks, go all the way down, all the way up. If there is stronger winds, that puts people in danger. So yeah, being able to do this from, let's say, comfort of a boat would be a big benefit.
But it also sounds very complicated.
Yes, it is very complicated. So originally this was the idea behind the company. But yeah, we realized that this is very ambitious as a project, and we need to work on it, let's say, piece by piece. So yeah, we decided to switch the focus from the full drone to just a flight controller. And flight controllers are interesting for several different use cases. In general, the drones are used for reconnaissance, they can be used for inspection, they can be used for delivery. So yeah, these are the use cases we are seeing so far, but there'll be probably more as people come up with new ideas how to use this technology. And yeah, our mission, let's say, is to make the next generation of flight controllers with focus on ease of use, flight performance, and safety.
Okay. Guess this hints at why Rust is such a nice language for flight controllers, but maybe if you can say it in your own words, given that flight controllers have existed before and probably they were written in other languages like maybe C or C++, I don't know. What's the new big idea that Rust brings to the table now?
So Rust is interesting in terms of flight control because it focuses on some of the same things which are our goals. So that's the performance, reliability, and productivity. So that, yeah, a lot of bugs which we could make in other programming languages are impossible in Rust because of the type system, of the memory safety, of the thread safety.
Yeah, because those drones, they can't really be operated remotely. They are operated remotely, but like it's kind of a problem if they crash or if the software fails, because that could mean potentially that you harm people or you harm the device at least, and you kind of want to avoid that. Like a seg fault in the air is probably not a good idea.
Yeah, you definitely don't want things crashing in software, also not in hardware. So yeah, if something goes wrong and you can't continue flying, that means your drone will probably hit something. There will be material damage. So if you're lucky, it might be just a few €100 to replace some parts on the drone. If you're unlucky, it might actually harm somebody.
But what happens if you have a situation where a rotor, for example, breaks? This is something that is completely outside of your control. How would you handle such a situation in the air?
Yeah, so it's not that common that a rotor would break completely. A more common is that the ESC, that's a chip which controls the motor, burns out, or the motor just stops working. And yeah, we have a few different approaches for that. One approach is that we are getting the feedback from the ESC, it's the motor controller. So we know how fast the motor is spinning. And if we lose this information, we know something's wrong. And what we can do is we can reconfigure our flight controller to use only the remaining motors and keep flying. This is possible, for example, on hexacopters or octocopters, which have a lot of different motors. It's very challenging on quadcopters because it's very difficult to fly with only 3 motors. You basically need to start spinning really, really fast, which you could argue makes the drone more dangerous. But yeah, this is the area of research. But for drones which have enough motors, we can just start ignoring the motor, turn that off, and use the remaining motors to continue flying or, let's say, do some failsafe maneuver.
Yeah. So from a technical perspective, or maybe from a software architecture perspective, how does it work? All of these detectors, they have to run somewhere, and I assume they run on the controller, and it's not enough to have a single detector for all the rotors, because essentially you need to kind of monitor all of them separately, because they are individual rotors. They could break at any point in time and like separately. And I do wonder, do you run these things in parallel on the controller with different threads, or do you have a different way of running all of these detections more or less in parallel? And also, for how long do you keep the incoming signals from the rotors, for example?
Yeah. So this detection I was talking about, it's still let's say prototype or area of research. So nothing is really set in stone. But in general, you need to run several different things on the drone at the time, on the flight controller at the time, to maintain the operation of the drone. The way we are doing it is that we run several different services in different processes, and each service outputs a certain information, and that's consumed by different services. And together, the data flows between these services from the sensors and from the remote control all the way to the output to the motors.
Do those services run in separate threads?
Yeah, those are different Linux processes.
Mm-hmm.
So we are running this on Linux, and generally each service is a single thread which just runs in a loop forever and reads the data it needs to read, does its thing, and then writes the data it needs to write.
Okay. I'm kind of surprised that it's an entire Linux system there. I thought that there would be problems with battery life or maybe with hard real-time capabilities, but maybe that's no longer the case. Maybe modern Linux operating systems work really well in such environments.
Yeah, so currently we are using Compute Module 4 from a Raspberry Pi to run the Linux side.
Mm-hmm.
There are 4 cores, and for the scheduling, we are using Deadline Scheduler, which is quite robust. And for each process, for each thread, you can request a period. How often do you want to run? You can request runtime, that is, how much time you want to use within each period. And the scheduler will make sure to wake you up at fixed intervals and make sure that it allocates to you enough runtime to do your thing.
Mm-hmm. That means if you already have all of those capabilities, how does the software look like? The Rust code itself, is it structured like any other, say, backend Rust application? Do you have any limitations on the crates you can use? Can you use something like Tokyo or async Rust in there? How does it look like?
So in the core part, we don't really use async or Tokyo. The flight controller runs at 1 kilohertz, which means that we have 1 millisecond to do what we need to do within the loop. And usually that's less, that's like a few hundred microseconds. Then we sleep and let the other services do their things. So running at this frequency means that, yeah, we need to be quite careful about how the individual services are scheduled. That's why we use the operating system scheduler, which can provide this to us. But we are still exploring to moving to more hard real-time operating system in the future. But for now, for the, let's say, lower volume production we have right now, we are using the compute module with traditional Linux, which has been working fine for now. But we are exploring options to move this to a more real-time operating system. But to go more into detail into this, the services are not that fancy. We use standard library. The service usually starts, opens some files where the other services are writing their outputs, and then runs in a loop forever, reading the files, doing some processing, and then outputting again to its own file. And yeah, we don't use even that many things from the standard library. It would be possible to make it just no STD, but sometimes it's nice to have certain features from there. So yeah.
Do you use any external crates, or do you only focus on the standard library?
We use external crates to, like we don't want to do the work which has already been done by other people much better than we would have ever been able to do it. So we use generally quite popular crates which are well maintained. We are keeping an eye on the stability and on the maintenance of those. We are using a cargo deny to check that all our crates have compatible licenses, that we don't use several different versions of one crate. We don't use yanked crates or crates with security issues. So that helps a lot with managing the, let's say, all our dependencies.
Mm-hmm.
But yeah, in general, we use crates like anyhow, this error, and algebra is a big thing because we need to use a lot of math to calculate everything. For interfacing with the operating system, we use Nix. We use Sin and Quote for procedural macros. we use ArrayVec a lot because we don't really want to allocate in our services. Few allocations here and there are fine, but if possible, we want to avoid allocating. So we use ArrayVec, which is on stack, and it has a fixed size. And we have bounds on how big the vectors can get, so that, we don't have to do any allocation there.
That means a lot of checks can be done statically because you know at compile time how big your data structures are going to be. That's pretty nice.
Yeah, so that's a big thing. We want predictability. We want to do as much checking as possible during compile time. And that also means we don't use that many boxes. Most of the things are enums. If we need, let's say, several different modes to do one thing, usually we put an enum there.
In aviation, there is a rule. I don't know if it's true for all the vendors, but it was kind of fascinating to me that when the machine, like the plane, boots up, not even flies, but when it starts, there's a promise that there won't be any more additional allocations. So everything has to happen on the ground, more or less. And maybe you don't have to go to such extremes, but I feel like there's the same energy with what you described, where you want to avoid allocations as much as possible.
It's certainly the same kind of energy, but for us, it's not really that strict. We can allocate if we want to, and if it runs fast enough. But every allocation puts certain uncertainty in your runtime.
Well, why is that? Maybe to explain to someone who might not know about this. Why is an allocation a risk, especially a dynamic allocation on the heap?
Yeah, so if you have variables on stack, they are it's known at compile time how much space on the stack the function needs. When you call a function, the stack gets expanded to include all the variables you're using there. And when the function ends, to put it simply, the stack goes back to the previous size. With a dynamic allocation using box, for example, or vec, there has to be call to the allocator, which is a piece of software which keeps track of which parts of the memory are empty. And it finds an empty place of the size that you requested, and it gives it back to you. And when you're done with that memory, you have to go back to the allocator, tell it, hey, I'm done with this memory. Please take it back, make it free again so it can be used later. And that's another call to the allocator. And there are a few things that can go wrong with it. I think the main one is that you run out of the memory.
Mm-hmm.
And then your allocation fails and you crash, basically. That's not that big of a problem for us because we don't need that many memory to run. We are maybe using 10% of the RAM we have, probably even less. So most of our core services can run with very little memory, actually. But this tracking of a free memory can be unpredictable.
Yeah, I guess that's a core point, also predictable performance, because on a stack, allocation more or less takes constant time. But on the heap, that's no longer the case because, as you said, you need to find a free page or multiple pages even where you can put your object. But like this can sometimes take very short time, but sometimes it can also take a long time, especially if you have a data structure like a vector that might need to be moved to a different location then to like fit into memory and fit into the space. And that is a bit of a problem.
Yeah, so vector has, let's say, additional danger there. If you keep pushing elements into the vector, into a vec, at some point it will need to grow. Usually it doubles its size, so it doesn't need to reallocate for every element because that costs time, that costs resources, and it would kill your performance. So as you push more things there, the vector needs to be relocated. The old memory has to be freed, and the data has to be copied over. So a trivial thing like pushing one element into a vec can have a big influence on the performance. If you have 1,000 big elements in a VAC. You push one extra, it pushes it over the capacity. Then new memory has to be allocated. Everything has to be copied. Old memory has to be freed. So, yeah.
What are some other areas where you would say people that don't deal with systems programming don't know much about these things, but they are very relevant to your line of work? So we talked about allocations, but maybe the other part that I was curious about was error handling. Because, yeah, it's not just maybe easy enough to just add a question mark and then propagate the error to the caller, because at some point there won't be any caller anymore and you want to avoid a crash. So probably you need to be extremely careful, or at least have a crash loops which kind of catches all of the bugs and then maybe restarts the service or something like this.
Yeah, so in general, if there is error in something essentially you really need, like, okay, we need this data, we need to read this data to perform our function in this service, and the data which is in a file is in incompatible format, for example, which can happen if you compile your services independently from different versions of your different Git versions, let's say.
Mm-hmm.
Then, well, there's not much you can do. This drone can't fly, so you just question mark it out of the main, and you can't do really anything. But the focus is on, yeah, if we really are in a situation where we can do anything, crashing is the best option rather than having a drone with spinning motors doing something which we can't control. But in general, for all the error cases, you kind of need to handle them as a regular, let's say, flow of the as a regular control flow. So if something can happen and you can handle it, then it's part of your software. You have code which implements that functionality, and yeah, that error case is handled and the drone can keep flying.
While you explained, I had two questions. First was, how do you test this? And second, how do you document this? Let's start with documentation, because when you started with this project in 2017 and like it's been ongoing, you probably uncover a lot of edge cases and things that might not be documented by the vendors, or your hardware behaves differently, or maybe you also just want to have your documentation very close to your code. Do you use Cargo Doc extensively to even document that, your edge cases, even if you use those libraries internally only?
Yeah, so in general, we do write documentation around our structs and around functions, especially when there is some assumptions or something which cannot be encoded in the type system. You have to mention it somewhere, otherwise this knowledge gets lost and you will run into some issue in the future. Or when somebody tries to fix something, they will break something else because they didn't know it works like this. But general approach is to encode as much as possible in the code, in the structure of the program, in the types, and make it impossible to compile it when your assumptions are not correct. Sometimes this is difficult or really unfeasible, so you end up writing docs like, okay, this can't be called here, or this can't be called with these values, or something like that. But in general, the preferred way to do this is to encode it in a type system, and that really gives you the peace of mind that it can't be misused.
Mm-hmm. What you're trying essentially is to make illegal state irrepresentable.
Yeah, so that's a big thing, is to be able to represent only valid states of your program, but also be able to express them on or represent them in a unique way. So your program is not in the code. Your program is let's say a conceptual thing, right? The logic, how you design the things to work, you can explain it on a whiteboard without writing any code, right? This is a place where logic bugs occur, right? You designed the thing wrong. You didn't take into account something.
Mm-hmm.
You have a logic bug, right? But then you can't run a drone on a whiteboard drawings, right? You need to encode this in a source code.
Do you use any patterns in the code? Can you give me an example for how such a thing might look like? Making illegal state irrepresentable, that is?
Yeah, so generally you want to structure the code in the same way as you had structured your program conceptually, so that if you need to make some change in how the things work on a logic level, you can go into the code and find a place where this piece of program is implemented and change it there. So about the patterns, I would say we have, let's say, we run into certain problems and we have certain solutions how to do them. Some of them are used more frequently and they are maybe what you would call a pattern. For example, we use a new type pattern a lot.
Mm-hmm.
This relates to, if you've heard of Boolean blindness, for example.
Can you explain it?
It's an idea that, okay, let's say you have a function which takes a Boolean parameter, and it can be true and false. But in and of itself, it doesn't have any semantic meaning. You see true and, okay, it's a value, but what does it mean, right?
Mm-hmm.
And this leads to code like, okay, somewhere is a function call and there is a true as one of the parameters, but you have no idea what it means.
Mm-hmm.
What you would do is you would create an enum, which represents the different cases, give them a names, and suddenly everything becomes much clearer. It's harder to make errors. It's, let's say, self-documenting. If there is a third case, you can just add it to the enum in the future, and it's easily extensible. And the same thing, a lot of people stop with just the Booleans, but this is the case with all primitive types. If you, let's say, if your function takes a float, it also doesn't really mean anything. It's just a number. You can add kilograms with numbers of apples, and it doesn't make any sense, but the type system allows you to do that. And you can mix it up because we are all just people. We make mistakes. So by using a new type, you can make sure that you can encode in a type system that, okay, this number represents number of apples. This number represents weight in kilograms. And the code is much easier to read because you know what things are when you read the code. And also it gives you place to implement the functionality on the type itself. So for example, you, convert it from kilograms to grams. Okay, you have a new type and you have a place where you can implement your function to do something with that value. If you use just a primitive type, you don't have that place. You end up with a lot of functions which, let's say, do something with the weight, but they're all over the place. And this is kind of a maintenance problem.
Yes, and this happens to the very best of us. For example, in 1999, the NASA Mars orbiter, which was used for, measuring the atmosphere of Mars, I guess, and was famously lost because of a metric bug. And yeah, that sort of thing can happen all the time. That cost 125 million. I just looked it up, which is kind of, quite a lot of cash.
And I think at least 4 years or even more in development and actually running the mission, right?
Yeah.
So yeah, if you can make your code not compile, if you make a mistake like that, and it doesn't have any effect on runtime, right? Because all of these types just go away when you compile the code. They don't exist in the output. Then it's hard to argue against this, right? It seems like a no-brainer.
Do you use the type state pattern as well? Maybe for some explanation, the type state pattern is when you have a generic type and it takes a t as an argument, and that t represents the state you're currently in. So when the drone is on the ground, it has a different state than when it is in the air, for example. And that means that some methods are just not available in the air. No, you can't call them. And that points out logic errors. Do you use that pattern in your code?
Yeah, I'm familiar with the pattern. I would say we don't use it very often because The controller needs to be quite uniform. So in every loop, you have the same set of data which are coming in. Some of them might not be available, but you can represent this with options or enums or stuff like that. And you need to output the set points for the motors.
Mm-hmm.
In every loop, let's say you have to perform, you have the same inputs, same outputs, you're calling the same function, but the state would be represented maybe by a different variant of an enum. So if your drone is not armed, we have a state that maybe the motors are not even connected, and we just check for signals that we should switch to a different state.
Mm-hmm.
Once that happens, we switch that enum to an armed state.
Mm-hmm.
On entering that state, we initialize the motors, make the connection, start sending the signal to them. And from then on, every update is processing those data in a different way.
Right. So it's essentially the same thing. It's a state machine where you need to transition between the different states.
Yes, I would say there is many. The core loop is a state machine,
mm-hmm.
but there is a lot of different stages to that calculation.
Mm-hmm.
And the different stages can operate in different modes. So based on how you want to fly the drone, for example, you want to control the position of where the drone is. In a different mode, you want to control the angle of the drone, how much pitch and roll is there. And for this, I'm not sure if it's exactly a pattern, but we represent the communication between the stages happens with enums. And the controller in the next stage looks at the enum and switches to the appropriate mode to be able to handle that command. Initializes the state for that mode and then stays in that mode until it's switched to another mode from the upstream controller. This might be let's say, a pattern which we are using quite often.
Yeah, and it is a very common pattern that I see being used in other environments too. And yeah, it's great to hear that you can use that even for drone controllers, and that's kind of cool to know. Do you use any unsafe code, or is it completely safe Rust? I mean, when you control a drone, you kind of need to interface with the hardware at some point. So I do wonder if you need to use unsafe for this, or if you can go through maybe other ways, like connecting to the pins with files, or some other way of I/O that doesn't require unsafe.
So in general, we try to isolate the unsafe to, let's say, library crates,
mm-hmm.
so that we can write tests for the crate, we can ensure it works correctly, and then we don't have to deal with the unsafe on higher levels.
Mm-hmm.
I guess that's a pretty common approach in Rust.
Mm-hmm.
Either there might already be a crate which does what we want, so in that case we might just use that crate. In other cases where we need something more custom, we use unsafe. We use a lot of unsafe in certain levels because those operations are inherently unsafe.
Mm-hmm.
And if you don't program them correctly, you might introduce undefined behavior, or it's really the places where you need to say, like, okay, I understand this is dangerous, but I promise I did it right. And you write the tests to do it, you test it properly, and you keep an eye on this, but then it's solved and the rest of the code doesn't have to deal with that.
Speaking of which, let's talk about testing for a moment. Can you test most of the logic with unit tests, or would you say you need a lot of integration tests and functional tests? Or would you say that you can test on a much lower level with a smaller scope through unit tests?
So the testing, different pieces of code are, some code is easier to test, some code is very hard to test.
Mm-hmm.
For the library crates, we write unit tests, we write integration tests. They run on every commit on our CI. So without everything passing, we can't even we don't even build the code.
Mm-hmm.
So a lot of our code is split into crates which are tested. Some higher level crates, for example, you have a crate which does a PID control. That's a very popular form of a control loop. That's one of the algorithms we support. And for that, there might be a test which gives it a series of inputs and then checks that the outputs match what's expected of this algorithm to output over time. So, yeah, we run little tests faster than real time by using, let's say, virtual time.
Oh, okay.
We run it through a tiny simulated scenario, which we already know what the inputs and outputs should be, and we check this in this way.
Nice. That's very nice. And once you have a case which you haven't, covered yet, maybe you found an issue in the wild, can you also recreate that in the lab and maybe make this a test for the future?
Depends really what the issue is.
Mm-hmm.
A lot of the time sometimes it's purely a logic bug, and then you can look at the flight log, for example, and you can put your detective hat on and see what went wrong and follow the data through the code and see where might be a logic bug. And then you can try to replicate it and see if you fix the problem or if it's somewhere else. But in a lot of cases, it's a problem. It could be a problem in hardware.
Mm-hmm.
So, for example, some wire is loose. There is not a good contact, but a lot of the communication is using digital protocols. So it works quite well until it suddenly breaks down as the connection really breaks. So in those cases, when there is something strange happening, the general approach we are using is add extra logging, make sure we have those diagnostics, try to replicate the issue, make sure we have the data logged, and then try to mitigate the issue.
Can you log that data remotely? Say a drone is in the air and it crashes, you want to know what happened right before. Do you have some sort of black box on the device, or can you even send the logs over the air? How does it work?
We have some telemetry which can be viewed remotely.
Mm-hmm.
However, we don't generally use this for logging. We write a log file on the drone itself,
mm-hmm.
and we flash it quite regularly so that in case the whole thing loses power or something, we don't lose much data. And we log a lot of debug information. We log all communication between the services. So we use shared memory for communicating between different processes. And we also have a logger which can scrape all of the data and save it in a structured way into a log file. So in general, these log files are what we use to diagnose the issues after the fact.
One other thing I wondered while you explained was, do you use a lot of traits to mock controllers? For example, you have a real implementation that works against a real piece of hardware, and then you have a mock implementation which you can use for testing.
We don't use mocking a lot. In general, we write a driver for something or a piece of software which does a communication, and we usually just test it thoroughly with the hardware. We check with the specification of the interface or piece of hardware which we are using, make sure what we have matches the expectation and not what we might accidentally see it doing, because that can be also a big source of bugs where instead of following the specification and what the different functions promise to take in return, you rely on the current behavior and the current implementation. Or maybe you get different hardware revision of the sensor, and because you didn't rely on the specification, it might suddenly break. So I think that's the approach we are currently taking.
Speaking of which hardware gets used in your environment? What are the things that you have to deal with out there in the wild?
So our flight controller, we also develop the hardware ourselves.
Mm-hmm.
So we have a nice PCB with sensors and STM32 on it.
Mm-hmm.
And as I said before, we use the compute module at this stage, which clicks into the board. And yeah, the board has several different interfaces. There's UART, I2C, CAN, Ethernet, Wi-Fi antenna.
And do you use any hardware abstraction layers for the STM processor?
Yes, the firmware which we run on STM32 is, we try to keep it quite minimal because it's quite difficult to log data from it, to have visibility into what's happening there. And in our use case, it's mostly used for I/O. So the STM32 is the thing that communicates with the motors. It has an implementation of the protocols that are used for communicating with the motors, like PWM or DSHUT. And it's also responsible for reading some analog inputs. There are some UART connections for remote control. So yeah, these are the main ways in which the STM32 is used. For now, the firmware is based on STM32F4XX HAL. And yes, I think the HAL is quite, let's say, everything has a different type. And if you want to treat certain things in a uniform way, sometimes there is maybe missing trait, which doesn't allow you to treat all of the maybe pins or some other peripherals in a uniform way.
Would that be something you would like to change if you had the luxury of rewriting that crate? Would that be something that you would introduce, or is it a limitation of hardware itself and it's just not able to be used like this?
I think this is a design decision of the crate, and this code was originally written maybe 4 or 5 years ago. And of course, we've been maintaining it, upgrading it to a newer versions of the crates over the years. And I can see that the way we think about how to program embedded systems is evolving. And I think the structure of the crates available also reflects the way in which we think about this and what we actually want to encode in the type system, what we might not want to encode there, because it makes the life of developers much harder, for example. So yeah, sometimes you run into some edge case which nobody else ran into. That's like, oh, I would like to do this with these 16 pins, which are controlled by 4 different timers, which each use a different DMA channel and stuff like that. And sometimes it's a bit of challenge to make some trait for it, or in the worst case, you can always use a macro to implement all of this. But it's a bit hard to work with. It breaks the code navigation, and we try not to use the macros for this if we don't have to.
So your colleague, Mara Boss, she's very famous Rust Hessian and I guess also a Rust team member. She wrote a book, Rust Atomics and Logs. So she is definitely a big proponent of open source. I do wonder how you maybe contribute back as part of Fusion Engineering. What's the mindset there? Do you fix bugs upstream? Do you maybe contribute in other ways? How does it look like? How do you think about the Rust ecosystem as a whole?
Mm-hmm. Yeah, so in the crates we are using, if we find some issue or some bug, or if we need new functionality, we tend to fork the crate, implement a fix or implement new functionality, and submit it upstream. These crates are usually in our GitHub repository, which contains the forks. In other cases, when we have some functionality which we think could be useful to a broader Rust ecosystem, we turn it into a public crate. So, for example, we have an inline Python crate that allows you to run Python from your Rust.
Wow.
That's quite useful for plotting outputs of simulations and stuff like that. We have an int bits crate, which allows you to set individual bits or access individual bits of integers.
Oh, wow. Okay.
Which is useful for if you do any drivers for any hardware, because usually each bit means something else and you need a nice way to access them. And one more crate we are using quite often is a Git version, which allows you to compile in the Git version of your code into the program itself, so that we can we can use this, for example, to ensure that our version of the STM32 firmware is the same as the version of the service that runs on the Linux side. And if it's not, we can refresh the firmware and make it synchronized.
That means you use that information for reproducibility. You want to know what gets shipped and what the firmware contains. You want to have like a build order of materials for your drone software.
You could say that.
Mm-hmm.
We tend to ship everything together from a single commit so that, we don't run into these issues where things are different versions and they don't match.
Can you update the controllers once they are shipped? Can you reflash the memory in the field? How does that part work? Let's say I buy 100 drones from you, or drone controllers, that is, and then I want to keep them up to date because maybe there's a fix or some critical issue that I want to have patched. Is that even possible?
Yes, it is possible. We have a way to check for updates and install them using Package Manager.
Mm-hmm.
We're still working on the fleet management. So if you have 100 controllers, it's probably going to be still some manual work to update all of them. But we do have update server, and we do have a release pipeline from our GitHub where our CI builds test builds, which we can immediately download to our drones. But we can also release build after testing and fixing everything, which then can be downloaded on the flight controllers used by our clients.
That's pretty amazing. And you build all of that in-house, the package manager for that, and the uploader and so on?
For now, we are using a package manager of the Linux distribution.
Oh, wow. Okay.
Yeah, the server builds the packages, updates them in its own repository, in a private repository.
Mm-hmm.
And then the flight controllers can access the new versions.
Way more modern than I anticipated. Kudos to that.
Thank you. But we're also working on a way to update it offline just by connecting directly to a computer. But there are still some improvements in how all of this could work, and we learn more as more people are using our flight controllers, and we see different use cases. So, yeah.
It sounds like Rust was a big investment for the company, but it also paid off well, I would say. How often do you need to drop into C and do FFI things? Is that something that you even have to do, or can you use Rust for everything and you're pretty much covered now?
So when the company started, that was before I joined the company, we were using C++, but it turned out that we have quite a multidisciplinary team. You need software engineers, you need control engineers, which know all the math of making things fly. You also need mechanical engineers and people who work more with the hardware. And it turns out for people who don't have a lot of experience, who are not professional software engineers, learning C++ can be quite difficult. And it's very easy to, let's say, create bugs or memory violation, access violations, or stuff like that. So we tried to use Rust, and it turned out that the people who are not professional software engineers can pick it up quite fast, can be productive with it quite fast, and the code quality is much higher because Rust, usually there are idiomatic ways how to do certain things, and there is not like 15 ways to do one thing, which changed over the years. That's maybe thanks to also Rust being a younger language, which doesn't have that much of a baggage. So the benefit for us was that more people on the team are able to write code, and the quality of the code is, I think, much higher.
Wow, that's a nice testament to Rust. And if I understood you correctly, that also means that you can bridge the gap between different disciplines or departments. You have the electrical engineers, you have the high-level software engineers, you have the people that know how to use simulation tools, and they all speak the same language.
Yes, that's right.
It's pretty impressive.
Yeah, I think so. And Yeah, the Rust already comes with the package management. It comes with the testing. It comes with the formatter, documentation generator. So all of these things make everything much easier. People can read the Rust book, or there's very good documentation for all of these pieces of the Rust ecosystem. And we are basically using all of this.
Do you see Rust spreading across the industry from your line of business to others? So maybe related fields like, as you say, maintenance work for industrial machines or turbines or things that are kind of, very complex pieces of machinery, and you want a common language to talk about a system across disciplines. And do you see that happening? Is Rust on the forefront here, or would you say it still requires time?
I'm not really familiar with how this works in other disciplines. I can imagine that Rust is getting there. People are becoming aware of it, of the benefits. There are initiatives to make a Rust easier sell for mission critical applications. For example, Ferrocene, which is a project of Ferrous Systems. And yeah, I think there is a lot of work underway to make Rust more suitable for these critical applications. And people do notice, they investigate, but I think a lot of this code can be very old, especially the infrastructure code. For example, you have railway infrastructure, and some of this code might be decades old even. And any change there is very risky, and it has to be very well thought out. And yeah, for these extremely risk-averse use cases, it might still take some time for Rust to enter the game. However, I think people, as I said, are becoming more familiar with it, seeing the benefits, and maybe introducing it bit by bit into their current systems.
Amazing answer. How do people even get started with such an endeavor? Because I wonder if it's a very accessible field for people who only know Rust right now.
To be honest, when I joined Fusion Engineering, I didn't know anything about drones. Absolutely zero. But yeah, as I said before, I had some experience from interactive applications, and turns out that's quite useful when you're working on drones, because even though the flight controller runs at much higher frequency than your typical game, 1000 hertz versus 30 or 60, I think the general structure is very similar, and we care about similar things as game developers would, which means you need the predictability, you need to get your frames out in time, same as we need to tell the motors what to do in time. And the whole structure of looped services which run in ticks is very similar.
That is true.
Other than that, there is a lot of interfacing with different hardware and software. So being able to work with different protocols, serialization, deserialization, even network services, all of this can be really useful when working on drones.
Yeah, initially when you described the process of looping through inputs and then having these hard real-time constraints, I was sort of reminded of game development. I wanted to hook into that anyway. And you heard it here first. So if you have a background with Rust and game development, maybe drones could be something for you. And lastly, it has become a bit of a tradition around here to ask you if you have a message to the Rust community, anything that comes to mind, this is the time to say it out loud.
I would say thank you and keep up the good work. And yeah, I think together we can really improve how software is being built and the quality of the software in general.
I couldn't have said it better. Jakub, thanks so much for your time. It was a pleasure to have this interview with you. Thank you very much.
Thank you for having me. It was very nice.
Rust in Production is a podcast by Corrode. It is hosted by me, Matthias Endler, and produced by Simon Brüggen. For show notes, transcripts, and to learn more about how we can help your company make the most of Rust, visit corrode.dev. Thanks for listening to Rust in Production.